All right. Hello, everyone, and welcome to MAE146. This is the third discussion. First of all, I want to apologize for not being there in person. I'm at a conference in DC, so unfortunately, I won't be there for the entire week. So I won't have office hours as well. Um, this discussion will be about the homework. Hopefully, I can guide you through the entire thing. If after watching the video you still have issues, feel free to email me. I'll try to get back to it as soon as I can, but I can't promise anything because I'll be busy the entire week. But anyway, let's get right into it. Let's go ahead and pull up the homework first. So right here, let's start with the first problem 2.1. Two particles of identical masses are acted on only the gravitational force. So this is very similar to what we did last week, the example 2.2 that I solved during discussion. So let's just start with the same development that we did last week, which was we started with the diagram. So let's start with the diagram just to make things clear. We have M1 and M2, and they're separated by a distance D. Okay, then the problem is saying what is the angular velocity of the line joining them? So we want to know what the angular velocity of this line is. So what is this lowercase omega? And it's recommending us to use the Newton's second law with the center of mass of the system as the origin of the inertial frame. We know the masses are equal. That's given by the problem. So we know the center of mass will be in the center. Right? So equal distance from M2, equal distance from M1. So, and gravity is the only thing that's affecting this. So if you remember from my discussion or the lecture with the professor, when the gravity is the only thing that acts here, we will have the force that M1 does upon M2 and the force that M1 receives from M2. Again, just to reiterate, the masses are equal, but just to have the difference between directions, we're going to have F12 here and F21 there. What do we know here? We know you guys have seen the gravitational force. Force due to gravity is what? It's just G M1, M2 divided by the distance that separates them. We typically use R, but this problem uses D. So let's just use D. And then the vector that connects them. We're going to use a generic unit vector U. Why do I use U instead of D? Because D would be dimensional. U is dimensionless. We're just stating the direction. We don't want to add any extra scalar here. We just want to know the direction. This is a vector. What else? We know Newton, right? F equals ma. But what is ma? We have, if I drew just the line with the center of mass, we have some acceleration. And the angular velocity. At the tip, what do we know from rotational motion? If we have an acceleration or an angular speed, what's the linear acceleration? A, if you remember, is distance by time square, and this is radians per second. Radians, in a sense, it's nothing. It's no dimensional. How do we get this? So the distance A will be equal to some distance, let's call it R, and we have second square on the denominator. So we're going to obtain them from here. What is this? This will be the distance to the point, which in this case is what? This is D, it's D divided by 2. This is the acceleration. We can substitute this here. And we can substitute the force here. The problem is asking you to find little omega. I think you guys should be able to find it from here. Just to clarify, I'm just giving you hints to do the homework, but I'm not solving the homework. I'm gonna leave you the last steps for you guys to solve. If you submit just the things that I do during this lecture, obviously you're gonna have full grade because everyone can just copy what I do on the video. Show me that you go beyond what I do and find the actual answer. Don't just do what I do, because everyone can do that. Okay, so this is problem 2.1. Let's move on to problem 2.3. Okay, so what's problem 2.3? Let's go back to it. So, problem 2.3. Consider a two-body problem. So we're in the same problem, same setup. And then there's a force T, such a rocket thrust, acts on M2, in addition to the gravity that we were already doing. Then we need to show that the equation of motion of M2 relative to M1, this is important, relative to M1. So we're looking at the distance between M1 and M2 is not to the center of mass anymore or to that inertial frame that we set. It's relative to one another. And we need to prove that it becomes this. Okay. Let's go back to the paper. So we have the same setup. M1, M2. So right now we have a thrust force and we are not specified the direction. It can be any direction. So let's just put a general T like this at a random direction. And we also have again F21 and F12, right? Okay. What is the key here? The key is we're looking for the relative distance between the two. So if you look at previous problems, we called this little r, and it's a vector. So we want to know how this r changes with time. We need to know the differential equation. what do we know? Let's apply Newton on M2, for example. So on M2, what do we have? If we apply Newton, so summation of all the forces equals MA, what do we have? So the forces acting on M2 are F21 and T. And then equals to M2 times the acceleration. What's the acceleration? Let's look at the inertial frame to start. That was centered at the center of mass. So how did we call the distance between the center of the reference frame and each mass? We used capital R. So we have capital R2 there and capital R1 here. So this is going to be R2 double dot because it's the acceleration, right? What do we know about these? How are these R's related? Remember, we're trying to find as a function of this. So we can write R like this. Sorry, it's negative. Right? So let's substitute this in here. This will be R plus R1 Let's apply Newton on M2 now. Sorry, on M1. So we have the same thing, summation of forces equals to M1 times acceleration 1. This should be acceleration 2. What forces are acting on M1? This M1 doesn't have thrust, so it's just F12 equals to M1 times R1 double dot, following the same procedure we did here. So we now have the equation for M1. We can combine these two, right? This one and this one. We can combine them. And what do we know of F12 relative to F21? We know that they're equal, but in opposite directions. So we're going to apply that. We're going to obtain F21 plus T is equal to M2 R double dot. And here I'm going to substitute, I'm using this equation, I'm going to substitute R1 double dot from here. So that is F12 divided by M1, right? I can apply this. Sorry about that. I'm not going to keep going because then I'll be solving the entire problem. But from here, you need to find an equation for r double dot. Should be easy to find. You just need to keep going a little bit further. What else? This problem was also asking for let's go back to it. Yes, there's another question. If the thrust vector has magnitude t and is aligned with the velocity vector, then yes, when I read this question, I was a little bit confused because the question is giving you the answer. I think this is just trying to teach you that when you have a vector, so let's say it travels this way, and we have thrust in the same direction. If you're given the magnitude, and you're given that the thrust direction, this means parallel to the velocity, how can you express thrust as a vector? Thrust as a vector is the magnitude, and then the direction comes from the direction of the velocity. So we're going to multiply this with a vector. And this vector, let me call it u sub v. This vector needs to tell you the information of the direction of the thrust without changing the magnitude, obviously. So we need to multiply by a unit vector. That's why it's had this little hat. This hat means that it's a unit vector. Which means it won't change the magnitude. How do you do that? So it's thrust times the velocity vector divided by its magnitude. If you divide a vector by its magnitude, you have a unit vector. So this thing is giving you the information of the direction without changing magnitude. This is what we want. This is the solution of the question. I don't know why it's asking you to, like, it's literally giving you the solution in the question. Probably it's just trying to teach you what I just said, but oh well, let's just leave it at that. And to answer any potential question, yes, you will have full credit if you do this, because it's, as I said, the question is giving you the answer. Okay, let's go to the next problem. 2.4. Okay, this one is the one that uses MATLAB. So we have a satellite orbiting the Earth, and we're given the initial position and initial velocity. This all sounds like the problems we solved in class. And then it's asking you to solve the regular two-body equation numerically and find maximum altitude and maximum and the time at which the maximum altitude occurs. So let's do that. So we have the Earth, and we have a satellite. We have the initial position, three two zero seven 5459 and 2714 kilometers, and we have the initial velocity minus 6.532.7835 and 6.142 kilometers per second. So we have the initial radius and the initial velocity. Okay. And then we need to solve the two-body model equation, which is R double dot like this. Solved with MATLAB. Okay, this is very similar to what we did last week and the week before. Remember the first week we solved the car. The car had these variables. Last week we solved the two masses orbiting each other. So we had this we had a lot of variables. Right? What do we have now? We have radius and velocities, right? So that's what we're gonna be calculating. Allow me to call my unknown vector of unknowns. What do we have here? We have just one mass, which is a satellite. So my unknowns are gonna be six. The three positions and the three velocities. It's comparable to what we did last week, but we had two masses then. This time we only have one. So we have its three positions and its three velocities. How did we solve these problems using MATLAB? Let's find the derivative. Right? Easy, we've done this. So what is this? As we did last week and 2 weeks before, I sound like a broken record, but it's clearly what it is. I'm not saying anything new here. I'm just looking at this and noticing this is the same as that. And then what do we have here? We have the accelerations that are given by this equation. This is, remember what I said last week? This is vectorial. So you can break it down into X, Y, and Z. This is just more compact. So what is X, Y, and Z? X is minus mu divided by R3 times X, which is R1. What is Y? Minus mu divided by R3, R2. And what is Z? Minus mu divided by R3, R3. This is that, this is that, this is that. That's the acceleration x, y, and z. And this is what we input in MATLAB to integrate. Let's go to MATLAB and do it. Okay, here it is. Let's start from the beginning, just as we always do. Clear and close all. Okay. What do we want to do? We want to integrate. So let's just use the integrator, which is what? ODE45. How do you use ODE45? We first input the function that we want to integrate, which we haven't done yet. So let's just leave it like that. Then the t-span, so how long you want to integrate the equations. And then the initial position. We've been using R, so let's use R0. How do you, what's the output of ODE45? It's two things. It's the time and your variables, which we are calling R. So let's just stick to it. So that's what we're going to be doing. We're going to be integrating a function that we haven't computed yet during this amount of time, starting at these initial conditions. The initial conditions are given. So let's just put them here. R0 is equal to what? So we have the three positions and the three velocities. Okay, then t-span. T-span means how long you want to integrate the equations for. We haven't been given any hint. Well, all we know is that we have a satellite orbiting the Earth. So we don't know how much time we want to integrate. For sure, we're going to start at t0. And then what's the final time? We're going to be inputting this in seconds. Let's just say something random. Let's just say 1 day. So 1 day would be 24 hours times 3,600 seconds in an hour. So right now, the solver will integrate the equations for 1 day. If after solving the equations, we see that's not enough time, so we see the satellite just doing half a period around the Earth, then we'll do more. But if it's too much, if we see the satellite doing a lot of laps around the Earth, we'll just put less. I'm just putting a random number and then I'll adjust it afterwards. We need the function to optimize now. Sorry, to integrate. So let's do it. Let's do new function. What is the function? We're gonna call it satellite. This is the name of the function. What will be the inputs? So first we have the time, and second we have our initial conditions that we called R. What will be the output? The output would be dr, or r dot, or however you want to call it. Now we need to define dr. What is dr? We have it done on the paper. dr has 6 components. The first one is R4. Second one is R5. Third one, R6. These are the 3 velocities. Now, 3 accelerations, which are minus mu divided by r times r1. Minus mu divided by r. It's r to the power 3, right? Yeah. Times r2. And lastly, the z component. The function is going to ask us, hey, what the heck is mu? So let's do it. Mu is the gravitational constant. We're orbiting the Earth, so it's 398,600. This is in kilometer to the cube second square. And what else? R. R is the magnitude of the vector. So R is the magnitude of the distance from the center of the Earth to the satellite, which if you remember, we have X, Y, and Z, right? And if you have X, Y, and Z, which are R1, R2, and R3, that's how you find right? What am I doing here? Let me pause for a second. If this is the center of the Earth, and I have the satellite here, if I have X, Y, and Z, this distance, R, it's a radius. R squared equals X squared plus Y squared plus Z squared. So all I did was R equals square root. This is what I just did. You see, square root of X squared plus Y squared plus Z squared. That's it. We don't need anything else. Save it. It says that I already have it because I already practiced. It should be the same. So that's it, function. Then let's go back here. So we're gonna tell MATLAB to integrate function satellite. Let's run it and see what happens. Let me call it 2 because I already did it just to have another one. What happened? There we go. Okay, looks like it worked. So what's the output here? MATLAB gave us R. Well, technically T and R. T is the time. R is our variables. We can see here it's 100 times 6. Why 100? Because the function linspace breaks down the input time in 100 equally divided fractions, as I told you. We can specify this and be like, hey, I want more points, but let's not do it by now. And then 6, because it's your 6 components, x, y, z, and velocity x, velocity y, velocity c. We can double click this and see. You see, these are our initial conditions. It matches what we input, and then it integrates. So the first column, it's all the x. Second column, all the y's. Third, all the z's. Fourth, all the velocities x. Fifth, all the velocities y's. And z6, all the velocities z. So let's do a plot just to see how it looks like. Plot 3, because we're plotting in 3 dimensions. And let's do x, y, and z. So x is all the components of the first column. Y is r, all the components of the second column. And z is all the components of the third column. Enter. What do we see? We see an orbit. You see it's pretty ugly. What does this mean? This means we didn't pick enough points. This is what I was saying. It's a pretty scarce definition. We can be more accurate and get more points. For example, instead of 100, let's do 1,000. Let's see how it looks like now. You see it looks more smooth because there's 1,000 points instead of 100. What also do we see? We picked to integrate the equations for an entire day. And we see a lot of periods. So let's do less. Instead of 1 day, 24 hours, let's do just 8 hours. You see, it does less now. We still have 3, but that's okay. This should be good enough. So where's the Earth here? Let's make MATLAB wait, and then let's plot in the same plot the coordinate 0, 0, 0, because that's where the Earth is. And let's make it a black star. What do we get? The Earth is here. That means the satellite passes very close here, and this is very far. So this is what's called the periapsis, and this is the apoapsis. The periapsis is the closest distance to the Earth, and the apoapsis is the farthest distance to the Earth. I believe the problem is, oh, I don't know if you guys are seeing the plot, because Zoom sucks. Let me do this. Okay, let me go back. Let me redo everything, or at least the plots. So let me go back to 100 points in 24 hours, just real quick. What were we seeing with this? We were seeing a very ugly plot. This is because there's not enough points. How do you fix that? You add more points in here. You see it's more smooth now. And then we were saying that there's too many laps. We don't need that many. So let's plot less time. Instead of 24 hours, 8. You see, there's less revolutions now. And then I wanted to plot the Earth. So the Earth is there. So we can see that the satellite, it's closer here and farther away there. So the question is asking you to find the maximum altitude. So if we look at the plot, the question is asking us to find this altitude. Just a pointer. It's saying altitude, not radius. So this is radius. You need to do something to find altitude instead of radius. And you need to find the actual radius. It doesn't work just putting the finger here and looking at the coordinates. So I'm gonna leave you to try to figure out how. So what else? I think that's it for this problem. Yes, let's go to the next one. So for the next one, if the specific energy of a two-body problem is negative, so that M2 cannot move outside a sphere. Okay. So we're talking energy. That's my favorite equation. You'll notice after a few lectures that that's my favorite equation. Energy. What problem is this? This is 213. So energy. Why is energy so important? Because it's a conservative quantity, which means as long as there's no thrust, it doesn't change throughout an orbit. So you can have the Earth here and a satellite that does something like this. So a very elliptical orbit. It doesn't matter if you're here or you're there or you're here. Energy is the same. So this is very valuable because at any point in the orbit, the energy does not change as long as there's no thrust. If there's thrust, then you're putting in energy. As long as there's no thrust, the energy is the same. It also applies if you have a parabolic orbit. So at any point on the parabola, the energy is the same. I used different subindex on purpose because these are not the same. But in the same orbit, they are. So this is why the energy is so important. You'll use it a lot. In my advice for any problem is calculate the energy and save it because you will use it throughout the entire problem. So let's go back to the problem. So energy is negative. What does this mean? This means that the orbit is closed. So any orbit that is closed, so it continues, will have negative energy. Show that M2 cannot move outside of, so this will be M2 orbiting, and show that M2 cannot move outside a sphere. So we're looking at, this is M1. So the question is asking us to solve or prove that M2 will not go farther away than a sphere centered at M1 with radius mu divided by this. How do we do this? Let's go to the energy equation, the most important equation. Energy is equal to what? From physics in high school or whatever, you know that energy is kinetic energy plus potential energy. So it's the same thing here. Kinetic is 1/2 of mv squared. However, this is specific energy, which means it's energy divided by mass. So the mass goes away. So 1/2 mv squared becomes 1/2 v squared because we have gotten rid of m. And then the potential energy in astronautics is negative mu divided by r. That's it. So we know the energy is negative, and we're looking at the radius of this sphere. What happens when the distance is max? Or in the case that we wanted this to touch, or maximum radius, what will be the velocity? If this is max, this is 0. So let's isolate for r from here. It will be mu divided by 1/2 v squared minus e, right? So we're looking for the maximum radius. That's when it's got zero velocity, because if, imagine it's traveling away from it, for it to not have any more radius, the velocity needs to stop, right? If it had more velocity, then it would keep going. So we're looking at radius maximum, v equals 0. And I solved the problem. I'm sorry. Yeah. Do you guys see it? Do you see that for the radius to be max, we need to have 0 velocity, because if it had some velocity, then it would keep going. So we want to have minimum velocity, and that will give you the answer. Okay, let's move on to the last problem, and that is this one, 214. Relative to a non-rotating Cartesian coordinate frame with origin at the center of the Earth, spacecraft in a rectilinear trajectory has this velocity when its distance is that. Find the position vector when the spacecraft comes to rest. So, okay. So we have the Earth. We have a rectilinear trajectory. We have a given velocity vector 2, 3, 4. And then the distance is 10,000 kilometers. And then we need to find our vector when v equals the 0 vector. Okay. So what did I just say about the energy? If there's no thrust, the energy in this point, point 1, is the same as the energy in this point. The energy in point 1, we can calculate because we have the position and we have the velocity. That's all we need. It's kinetic energy plus potential energy. And then it's equal to a second point where the velocity will be 0. Right? So what is v1? We have the velocity vector. So let's calculate the velocity magnitude. That is the velocity magnitude. So here you can put in that. Then this is 0. And you can solve for R2. But this gives you magnitude. So it will only give us this distance in magnitude. But It's asking us for the vector. The only thing that I can say without giving you the answer is to remember the problem says it's rectilinear motion. So with that, you should be, with the magnitude and knowing this, you should be able to find this. Okay, so that will be it for today. Again, I'll be in the conference until Saturday, so I'll be a little bit busy. I'll try to answer your emails. Hopefully, this lecture helps you solve the entire homework. But if not, I'll try to respond to your emails. Anyway, I'll see you next week. Have a good one. Oh, and don't forget to comment, share, subscribe for the algorithm. See you next week.